to present our professor Jonathan Córdoba. He received his PhD in electrical engineering from the University of Campinas in 2017. In 2018, before joining the University of Federal of Minas Gerais, he moved to University of California in Santa Barbara, where he works as a postdoc researcher at the Department of Electrical and Computer Engineering. Currently, he holds an assistant professor position in the Electronic Engineering Department at UFMG, member of Brazilian Photonics Society, Optic, IEEE Photonics Society, and IEEE Circuits and Systems Society, selected Optica Ambassador, and class 2022, and IEEE Senior Member. Thank you very much. Jonathan, please feel free to start.
Thank you very much for your invitation, Dalton and Johnny, to talk today, but I think that will be very challenging to try after the nice talk from Sahir. I will try to do my best and explain a little bit about the light and different applications and situations that we came to meet from optics. First, okay. First, I would like to present myself. I am Jonathan Córdoba, just like Dalton said. I'm from Colombia, and I'm living in Brazil in the from approximately 2011. I'm from Colombia, and and my state department is in the Pacific coast of Colombia, and it's a beautiful place, really beautiful place, and it's the last refuge of native people and descendants of slaves. And in that way, we can see, for example, it's the poorest department in Colombia, but there are a lot of things that are very nice, and they're very nice people in that region, just like me, just like you can see. Yeah, and in that way, you can see the different picture that I take from my hometown. My house is very close to this place. Is the you can to how can I say you eat Colombia is, in that specific way. My hometown is very nice, and I will try to present myself in this specific way. Sorry. Well, I think about to put a picture in a little baby boy, naked and smiling, running, and in the rainfall. But I think that this is not a professional thing to do. For that reason, I will start talking a little bit about my preparation, my formation. And I am a computer and telecommunication engineer from the Universidad Católica de Pereira in Colombia. Later, I made my master. I got my master's degree in engineering in telecommunications in the Universidad Pontificia Bolivariana in Colombia as well, and my PhD in engineering, electrical engineering in the University of Campinas in Brazil. Well, later I stayed in like a visiting PhD researcher in the in the Catalan Institute of Nanoscience and Nanotechnology, and later before joining to UFMG, I was working like a postdoctoral researcher in University of California in Santa Barbara, US. Currently, I am an assistant professor in the electronic engineering department and in the engineering school. I'm member of the management committee of the nanomaterials characterization and processing laboratory. This is specific things that I would like to highlight because it's very important for the different applications and different procedures that I will to explain in my talk. Well, in the UFMG, we have different facilities that we came to use for the different kind of development of technology, taking into account nanomaterials and nano devices. For example, we have the nanomaterials characterization and processing laboratory LCP Nano in the UFMG, the SEX UFMG. We have the technology center in nanomaterials and graphene, and the microscopy center of the UFMG. I think that is one of the most equipped microscopy center in Latin America. This is very interesting because we have a lot of the facility is very complete for different kind of application that we came to implement in different ways and different types of implementations and in different research lines too. This is our research group, and we are working in different lines. We are working, for example, in localized surface plasma resonance using nanoparticles. We are implementing machine learning for different kind of application in computing application, or even in the physical devices. We have microscopy applications, electro-optical devices, and finally we are working in all photonic all photonic crystal based integrated circuit and system devices. Sorry. Yeah, this is our group, taking into account, for example, the professors that are belonging to the Altman lab, and the other professors that are working together. For example, another comment, like our professor Omar Paranaíba, that is here too. Well, to start my talk, I would like to talk a little bit the different kind of application that the photonics and optics have. And in that way, we can to see that we are interconnected, and the interconnection is a reality right now. We try to see, for example, that when you are trying to use a cell phone, you can see that you are trying to connect to different kind of devices, even in your house, in your car, in different places. You can to see that kind of application. For that reason, we are until 2020 was very important. That estimation that was made by the Optical Society of America, where we can see, for example, that the smart home until 2020 we to get $3.75 billion market for that kind of devices. That is any kind of device that you can to access in your home. For example, your freezer, you have your cam for the security and other kind of devices and that you can to access remotely. We can see the ongoing personal devices. For example, when we are using watch, cell phone, or another kind of device that you can to use for different kind of application or measurement, just like before, or Samir was saying, you can, for example, make the different kind of measurements for your watch. This kind of devices is very important because you can see the very different type of devices, wearable devices that we can to implement that kind of applications. Intelligent roads is another kind of device that we can to see. We have data-driven agriculture, and the most important, even after the COVID-19 pandemic, was the internet industry, because we can see the growth that specific industry had, and was very interesting, specifically because the data networks was growing and was making very most powerful for different kind of application, especially when we are obtaining right now, for example, the 5G technologies for telecommunications applications. But the big problem is that we don't have devices for that kind of technology that we are trying to reach in that specific way. The different kind of developments are must be directly for that kind of application. For example, we are trying to, inside of our group, we are working for different kind of applications that can meet with that necessity. For example, digital systems for all optical digital systems, telecommunication systems for electro-optical modulators that came to change the optical signals for electrical signals, right, to improve that kind of the interaction, integrated photonic devices to make a little bit smaller devices for different kind of application in telecommunication systems. We have components like smart devices, sensors for health agriculture and intelligent roads that is very important for the situation and reality that we are living right now. And finally, we have complementary devices that came to implement, for example, microscopy. SMIM is scanning microwave impedance microscopy, or TERS and SERS that are tip enhancement Raman spectroscopy and sulfur enhancement Raman spectroscopy that are using for characterization of different kind of surface or materials or biological systems to obtain information related to. Okay, in that way, I will try to make try to compilate that information and try to show you different applications that we are working on and what is the situation and the step that we are in this moment. First, we will to talk a little bit about the digital system or logical or optical digital systems, where we are trying to develop all optical digital gates for digital system, all optical digital systems. What is that? In a specific way, we have a device that is composed for photonic crystal devices, just like you can see here. These photonic crystal devices are devices that we have different ports. In this specific case, we have two inputs, and this input of the light is interacting inside of the optical waveguide, and through that interaction, we can to see an output related to the optical digital gate. For example, we can see an AND or NAND, any one of the digital system gate we can to implement. And in that way, we can see, for example, that devices, through the design, is possible to obtain that result independently of the type of the optical gate that you want to obtain. Just trying to maintain a specific design that will be behavior, we will to have a behavior for obtain the response that we want to obtain. In this specific case, I am trying to show one specific example of the switching, of the switch N and P combined to obtain that kind of result. For example, if we see that device in this cut, we can to observe the composition of the material that we are using for that development. We have, for example, 3-5 materials using for the confining of the light, and that confining of the light will to guarantee that the interaction inside of the optical path will be successful, and we will obtain the expected result. Specifically, when we are trying to guarantee, for example, the interaction of the different optical modes that you are interacting inside of that device. Yeah, in this case, for example, we can see the device as the response for the different interaction in the switch N for that specific device. The results of that work was published in collaboration with the Professor Roma Paranaíba and Professor Paulo Sergio Guimarães, that I incorporated in that work that they was starting before me, but was very nice to participate to obtain the result that we came to show in this papers. For telecommunication systems, for example, we have the implementation of devices that are interactive with different kind of materials, just like, for example, graphene. Graphene is a material, 2D material, very interesting for the electro-optical interaction, thermal characteristics, and the optical interaction with the graphene and the heat that you can to generate in optical waveguides is very interesting, specifically when you are trying to obtain electro-optical modulator systems. What is that? When you want to obtain the implementation of an conversion of the electrical signal for the optical signal, you need an intermediate system that will to generate that specific type of interaction. For that reason, that kind of modulators will permit you to do that, trying to modulate the signal, trying to obtain the response for that specific devices, and for telecommunication system is very interesting for that. And in that specific case, when you try to obtain this behavior, making, for example, here is double single layer of graphene, and we have between them and the silicon nitride layer, thin, approximately 20 nanometers, it's possible to guarantee the electro-optical interaction in that specific way, in that specific site, trying to obtain, for example, this kind of behavior. That effect is possible to apply to another kind of application, for example, biosensing application. For biosensors, for example, we need to guarantee a very strong electric field in the biosensing area. For that reason, if we have a much safer interferometer, when in the biosensing area we have a strong optical evanescent wave, it's possible to guarantee a strong interaction between analytes that we are trying to obtain and the interaction with the interaction of the light that we are trying to propagate in that specific devices. For that reason, applying, for example, that capacitor that we implement there was possible to increment the optical mode, trying to increased the evanescent wave, and was possible to increase the interaction with the external medium. That interaction generated a very strong sensitivity for that devices, and was possible to obtain the result related to that application. Yeah, was possible to obtain that applying electric and a voltage was possible to modulate the absorption of that material. For example, graphene is a very absorbing optical, will to absorb a lot of electrical optical mode. For that reason, it's necessary to guarantee that the absorption of that material will be very, very small. Trying to apply an electrical voltage was possible to modulate that absorption of that material, and was possible to obtain, for example, that trying to propagate in approximately 2 millimeters of optical waveguide with interaction with graphene was possible to reduce from nothing to almost 40 dBs of signal in the output of that device. It was possible to guarantee the transmission of the light inside of the device. Yeah, this work was published in the Clio 2021 and related with that application specifically. And trying to meet the expectation of this specific talk, I will try to focus a little bit with in this topic, because I will to talk about components related with the smart devices and how that smart devices are applying for application, for the medical application, biosensing application, and how we can to detect different kind of diseases, and specifically this is related with specifically this is related with the Aedes aegypti mosquito, okay? And just like dengue, Zika, chikungunya, that are very common in our region. Well, first, I would like to talk a little bit about the simulations that we need to do to obtain our device. We, inside our development, we are using different kind of methodologies to obtain a specific device that we will use for the detection applications of any disease. In that case, the numerical simulation is very important to do that. In the beginning, we are using final element methods that are used for simulation of natural phenomena. And that natural phenomena we came to obtain, for example, electrodynamics, biology of science that are very common for to do the different kind of analysis. And we are using the discontinued Gagliardi method or continued Gagliardi method that are the most common final element method solution that we came to implement. However, the time that we need to simulate complex problems is very long. For that reason, it's necessary to improve and try to obtain the better result as possible for that kind of applications. In that specific way, we are using for our simulation, complex numerical simulations using FEM is the final element method. We are using simulation implementing 2D models to reduce execution time. We are using batch simulation that is distributed in the processors for the different processors in the computer system. And we are using supercomputers. It's necessary supercomputer or cluster to do that kind of simulation. The problem is that not in any place you have all that infrastructure to do that kind of simulation. For that reason, it's necessary to obtain different kind of solutions to try to guarantee simulation, high quality simulations and high quality devices. For that reason, we are trying to integrate the numerical methods, in that case, final element method, neural networks, and genetic algorithms to do our simulation and try to reduce the time expend for to obtain our solutions. In that specific case, we have to define our problems and try to reduce our problem in a weak formulation and discretization that we guarantee our solution in the better way. Try to clustering our simulation problem and try to obtain our solution in the better way. When we are, for example, here is a simulate. This is an example of the simulation of the optical fiber. For example, we have, for example, that our simulation area is completely discretized, and we are dividing in different nodes, trying to obtain triangle space that are the final elements. That final elements depends on the area that we are trying to simulate. For example, here we have a very most complex region that we need to analyze. Is necessary to reduce the size of the element that we are using for our simulations. And depends of the quality of the mesh of the mesh that we are using, is possible to obtain the better result as possible. For that reason, if we are trying to use a 3D simulation, that mesh will be very strong and very, very heavy to execute in a common computer. For that reason, if we are trying to make the using, for example, neural network and genetic algorithms, just like we are trying to propose, it's possible to do the prediction of the different continuous element that we are implementing and try to obtain the result related with that specific relationship. That situation will permit that we are trying to obtain that as better as possible the result that we are trying to acquire for our simulation problem. And in that way, it's possible to guarantee a very strong and very most successfully and fast simulations in that specific situation. This work was developed for one of my students in the TCC, the monography in the TCC, and was very interesting because we are using right now for different kind of applications of our group. And why this is important and why we will to use that kind of situation, because we will to obtain 2D simulation and 3D simulation with very high and very effective way in the simulation problem. For that reason, for example, starting from that specific point, it's possible to translate that information in the devices that we came to develop physically. The neural network that we are trying to develop computationally is possible to translate and physically and try to obtain optical devices that will to behavior just like an optical network, just like in that specific way, taking into account the different core that device have and how we can to improve the interaction between different type of device components inside the single chip. For to obtain that specific kind of solutions, is possible or is necessary to understand the problem of how we came to obtain the behavioral interaction between optical devices and how that optical devices can interact to obtain the specific results in a specific application. For that reason, we analyzed and study nanoparticles for detection of dengue virus on the four different kinds of dengue virus and how that dengue virus is interacting with, for example, with Zika, chikungunya, and another flavivirus, for example, encephalitis or yellow fever, that are the most common kind of devices that are very close to dengue and Zika. And for that reason, we made all the procedure of the treatment of the surface of the nanoparticles. We are talking about devices around 38 nanometers per 10 nanometers of size, and was possible to obtain the devices and the simulation of that kind of devices and try to obtain the comparison between the simulation and the experimental result. Was possible. The result was very, very interesting. Why? Because when we are trying to do the measurement, just like we can see here, was possible to observe a very good correlation between the simulation and the experimental result. And that simulation and experimental result, we came to understand how how is the behavior of the nanoparticles when biofunctionalized will take for different kind of situation. For example, separation between the nanoparticles, thickness of the biological nanolayer, or the combination of the dot elements. That interaction was very good because it was possible to observe a very interesting interaction and how we came to observe and the reduction and increasing of the weight of the resonance in that specific case. I'm talking about the absorption of that group of elements. And that behavior is because the size and the separation, the size of the elements and the separation of between them. That behavior was possible or permit us to obtain a correlation between the different kind of dengue virus. For example, we came to observe optically that the dengue virus 1 and dengue virus 4 are correlated between them. And the dengue virus 2 and the dengue virus 3 are correlated between them. That is a very good starting point to understand that we came to obtain for other kind of devices, trying to trace genetic correlations with other diseases using our computational method that we are using in that specific situation. This is very good because when you have in a single space 2 or more types of dengue virus, or we came to increase the number of death, or the number of the cases that will affect the people in that specific regions. Well, in the same way, we did a clinical study taking into account the patient with dengue, without dengue, with Zika, and with another different kind of diseases related with that disease generated by the Aedes aegypti mosquito. And was possible to understand, for example, that with depends of the size of the virus that we are trying to detect, it's possible to observe a better or worse behavior at the moment of the detection system for that specific situation. And was possible to observe, for example, that the 3 is the smaller device, the smaller virus that we came to detect in that specific situation. It was possible to observe, for example, a very good correlation for the detection system for that specific device. Well, starting for that specific point, it's possible to understand that we have, for example, software plasma resonance is absorption about that specific kind of devices. And if we have nanoparticles or we have a surface, or metal surface, it's possible to observe in the surface that increasing or decreasing the angle of incidence, it's possible to observe absorption at a specific point. Because we have the movement of electrons in the surface of that specific device. In the other way, when we have the excitation of nanoparticles, symmetrical or asymmetrical nanoparticles, it's possible to excite the electrons oscillations in the surface of that device, observing the behavior of the absorption for that specific device. For that reason, when we have the detection system, the detection of the specific analyte, this is a protein or any kind of element that we try to detect, it's possible to observe that the resonance peak will be to shift for a specific direction. That direction depends directly of the size of the element and the behavior of the device, like a single element. For that reason, was possible to perceive that when you have a set of devices in a single layer on single surface, it's possible to guarantee that that device will interact in a single way. That interaction is very important to maintain always the same. And that interaction, you can to take a specific control of the separation of the elements and the size of the element. Guarantee, for example, in that specific case, that the variation that we have of the interacting electric field on the surface will guarantee that that meta surface will to generate the behavior and result that we expect to obtain. For that reason, it's necessary to take into account, for example, that we have different levels to try to analyze that specific kind of devices. Analytically, we can do semi-analytical analysis, numerical tools, or optimization methods and artificial intelligence methods for that kind of simulation obtaining of that kind of devices. Analytical, semi-analytical on the same way. Numerical tools are specialized softwares that we can to obtain to design our device, and the artificial intelligence method is the method that we are talking about here. We, in that case, we develop using the combination between the finite element methods in the numerical method and the artificial intelligence was possible to generate a set of data that we used, like the definition of parameters, neural network model training, genetic algorithm definition, and finally final set of generation. That pool of information, of that pool of that set of that transition will generate or will guarantee that we obtain the most efficient devices as possible with that kind of application. For that reason, when we study different kind of devices, we get a specific device with a specific size. Was possible, for example, just like you can see in this video, that it's possible to guarantee, depends of the size of the device, it's possible to obtain different diffraction behavior, and that diffraction behavior is important because depending of the behavior of that specific device, it's possible to obtain the absorption in a specific way. Well, that kind of devices can be used for the implementation of different kind of areas. For example, we can take devices for in the home activity and monitor activity monitors. For example, we have cameras that came to interact with the people, virtual assistant medical address, phone notification, especially with people that need to assist in the home. On the body, just like Samir said too, is you have devices that can stay on the skin or inside of the body. Depends on the type of device that you're trying to use. Or wearable device, just like a smartwatch that you are using commonly. We have within the community, and we have in the clinic and hospital facilities. In that case, we came to generate an ecosystem that can try to assist the people in different ways and different levels. For that reason, the development of biosensors that we came to implement for that kind of application is very important, and depends on the kind of devices and how that devices you came to implement for the detection of different diseases is very important to do. Yeah, the calibration of that device is very interesting. For that reason, I will to present here in the just one of the last work that we have is an LSPR based meta surface that we implement using the interaction between the light that is interacting with the meta surface, and we have generated optical oscillations on the pyramidal and on the surface. And that interaction between them is generate an interaction between optical modes inside of that device, depending of the angle of incidence. That variation was very interesting because was possible to see with the fabricated device that you can see here, that implementing for the detection of the PB27R is para, that name is very complicated to people. Paracoccidiomycosis is type of fungus that is very common in Brazil, and is the, I think, second or third cause of death in the here in the country. Yeah, is very very common, especially in the how can I say, the Rosa. Yeah,
Countryside?
yeah, the countryside. Yeah, right. And for that reason, it's very very important to know how that kind of diseases behavior in the community. And it's a not neglect, it's a neglected diseases categorized by the owner. That kind of behavior was possible to observe the behavior using the optical interaction and the Raman spectroscopy interaction. Using, for example, was possible to observe the response for the different kind of system that we was analyzing, and was very interesting to see the response of that specific device. That work was published recently by one group in ACS optical material, applied optical materials. Finally, we work with different kind of devices using microscopy, using, for example, scanning microwave impedance microscopy, or even TERS, is a tip enhancement resonance spectroscopy. That kind of application, in that specific case, I am presenting you the tip enhancement resonance spectroscopy. We was using that specific kind of application to characterize the surface of electro-optical behavior and response that we have with graphene. It was possible to observe that the variation of the charge on tip and the variation of the charge on the electric depends on the different kind of parameter, like a separation between the elements and the interaction between them. That work was published recently too, in the Optics Letter journal. And all this is an overview. This is an overview trying to show you how we came to implement the optics for different kind of application, using from the design of device that we came to implement to do different kind of analysis that we came to implement for different kind of applications. We have the fabrication of devices, the high complex devices, and the characterization using for understand the physical phenomena, the biological phenomena, the chemical phenomena in different kind of situation that we can to observe. In that specific case, it's possible to observe and understand that that kind of interaction could be interesting for different kind of application. And right now we are using in our ecosystem and our interacting group because it's a group between the electrical engineering. We have the engineering school, the ISEX, the ICB's biological institute. It's a very interesting interaction to try to obtain the different kind of response that we can to observe with that kind of devices with the the better response as possible for that kind of application. Thank you very much.
Jonathan, thank you very much. People, you see so many things that we can do with lights and applications, different things, devices, and really nice talk here. Anyone have any question here for Jonathan?
I have a question. What would you say are the greatest challenges in training neural networks using photonics in comparison with the
A lot.
current technology?
A lot. Well, you have we can to answer your question from two ways. The first one is the implementation of neural network for photonics. We came to implement from the computer way. When you came to take, for example, the implementation of algorithms to try to obtain devices that later you came to implement for a specific application. You came to complete your modeling with artificial neural network and numerical methods to obtain the better results. But the second way is trying to obtain the physical neural network. The physical neural network is a very challenging thing because currently, for example, we can see in the literature that the most advanced result that we can see is the inference. The inference of the neural network was developed photonics in the platform, but the training not. The training is the most complicated situation to do because you need the memory, and that in that specific case you need CMOS to try to implement the CMOS to try to obtain a memory. You can, and you in that specific way is necessary to do electro-optical conversion or acousto-optical conversion. Acousto-optical conversion, thinking about the quantum information and try to do the quantum interaction in that specific way, because you are trying to obtain from optics to electrics. In that way, you can to do it in that specific way, but it's very challenging because the most challenging thing is to obtain that specific component that needs the memory that you need to implement for that kind of applications.
Jonah, maybe some student has interest to work with you, and what is the profile, the desired profile for a student that wants to join your group and work? Can be electrical engineer, control engineer, hardware, software.
We are working with students from computer science, student for electrical engineering, student for systems engineering, student for especially from control engineering. Yeah, I think any kind of student from engineering came to study that kind of application because the basis of that is electromagnetism. Yeah, and even computational applied electromagnetism, you need to take the background of the electromagnetism.
I see.
Yeah.
And maybe these fundamentals can be learned in your course as well at the graduate program, right?
Yeah.
We have a photonics course
Exactly.
here in the graduate program that any undergraduate student can do, you know.
Exactly.
Uh,
Samir.
okay, Samir, please.
Very nice work, very breadth of topics you are investigating is like quite impressive. I will go to the sensing side because that's something I
Of
understand.
course.
So, because you're doing light based, you can do label free sensing, right? Because uh, you can just look at the spectrum, for example, of molecules you want to sense. You don't have to have a, like a binding kind of affinity
Yes.
based sensing. So, what have you explored in that front, right? I mean, I know the spectrum shows you some signatures, but do you need labels, or can you do label free?
Yeah.
And what is the limit there, and what can you not see, and what can you see? Just
Sure. Yeah, we need a label. It's not a label. It's a label free, but we are using the interaction antigen antibody.
you still are
Yeah, antigen antibody or DNA, RNA to obtain that interaction.
But you can also do without that.
Yes, I didn't do that specifically in this talk because it's not the focus, but yeah, we are working with that specific kind of interaction, and when we are doing that procedure to trying to functionalize the surface, all the biochemical interaction on the surface is necessary to guarantee the interaction between the gut and the different kind of material that we are using to make that ligations. And even label free, we are trying to obtain a characterization for each step that we are implementing in that application. Yeah.
Because your last one that you showed for characterization, the tip enhanced Raman,
Yes.
that can just sense for you because Raman is what you
This
use
one?
to characterize materials.
This one?
Yeah, something
Yes.
like that, right? So
Yes,
you
exactly.
don't need any labels for that when you're doing this.
In this case, not. In this case, it's just a drop on the surface. Because, for example, here we have the black line is outside of the preamp device that we are implementing, and the red line is on top of the pyramids that we are implementing there. But yes, in this case, we don't need the labels. But for the optical measurements, it's necessary trying to do the biosensing because without the interaction, it's not the biosensing.
Acho que vocês ainda podem conversar com o Jonathan, talk to him later, and it's easy to meet him. Muito obrigado, Jonathan.